Everyone, I'm Nazia Rahman. I'm a second year PhD student and I'm from Temple University. Today I'm going to present my work identifying benign and malignant breast tumor using Vibro-Acoustic Tactile imaging system. So why breast cancer? Why I'm working with breast cancer? Because breast cancer has become a great concern in the modern or in the current era of medical science. We have this data information available from Cancer's organization, and you can see that among different kinds of cancers, only breast cancer constitute 30%, which is higher than any other kinds of cancer. We have different kinds of cancer, but breast cancer is the highest one. And it has an incidence rate of 128.3 and death rate of 19.6 per 100,000 women. So as this rate is increasing day by day, so we have to find a way. So the only solution or one of the most important solution to reduce this mortality rate is the early characterization of the benign and malignant tumor. So we have already different clinical methods, imaging methods available to detect the benign and malignant tumor, but these methods have some disadvantages, including the overdiagnosis. So due to this overdiagnosis, many times people have to go through unnecessary treatment and screening method, which is not helpful or good for their health. And also these screening methods sometimes expensive and not accessible to every place or every country or everywhere. So that's why people are working to find a non-invasive way to characterize the breast tumor. And I'm currently working with find a non-invasive way to differentiate a benign and malignant tumors. So these are the outlines of my work, including the motivation, introduction, Vibro-Acoustic Tactile imaging system, and using this system, the size and diameter, changing diameter estimation, and finally to develop a risk estimation and the result. So introduction. So in the motivation part, I explained that why the non-invasive method to characterize the tumor is essential. So many research groups are already working with finding a non-invasive way to characterize the tumor. Our research group previously worked with the tactile imaging system. So to differentiate the benign and malignant tumor based on the mechanical properties of the tumor. And different other research groups, like from the University of British Columbia, they work on the mechanical properties of the tumor, and they also use vibration in their method. And it seems that with vibration, their tissue characterization process has improved. And other groups, they also work with vibro-acoustic system. And in that case, they apply vibration using air injection method, and they differentiate the normal tissue and tumor tissue. And they also prove that with vibration, that their tissue characterization process has improved. So based on the study or research we got, we apply vibration with our previously developed tactile imaging system. And in that case, we use ultrasound to create the vibration. And using this vibration, we try to improve the overall accuracy of our tumor characterization process. So these are our tactile imaging system that our research group has already developed. So the main parameters of our system is the LED as a light source, PDMS sensing probe, a camera to capture an image of the tumor, and this is the force gauge to record the applied force. So our tactile imaging system basically works on the principle of total internal reflection of light. So if you see this image, we have two scenarios. In the first scenario, there is no object or no tumor. But in the second scenario, we have an inclusion. So when there is no inclusion, you can say the light source from the LED totally reflected and no image is recorded in the camera. But in the second case, we have the inclusions, and due to these inclusions, there is a deformation in the PDMS probe. You can see this is the PDMS probe. So it causes some deformation in the probe, and due to this deformation, the light are no longer totally reflected. There is scattering of the light, and based on this scattering of the light, the camera captures this information. So this is our originally developed tactile imaging system. So these are the tactile imaging system, and this is our phantom, and tumor is included inside. And this is our tactile image that we got from the system. And our previously developed tactile imaging system, and in this system, we include the vibration. And these are the overall experimental setup of our Vibro-Acoustic Tactile imaging system. So firstly, we generate the ultrasonic signal in the range of 0.4 to 0.6 megahertz using the function generator. Then to boost the signal, ultrasonic signal, we insert the RF amplifier in between the function generator and ultrasound transducer. Then the boosted signal will send back to the ultrasound transducer, and this transducer convert this signal into the ultrasound wave. So when we apply the ultrasound wave into our phantom, it creates some vibration in the tumor. So these informations are what happens. So these informations are captured by our tactile imaging system. So if you see that this is the LED as the light source, and this is the same sensing probe. So whenever there is some force or vibration applied on the tumor or phantom, the sensing probe sends some deformations. So this information or this scattered light information are captured by the camera, and the force are read by the force sensor. So we have three different informations: time, force, and image. So these information are captured and sent to the data processing unit. So now the data processing unit works and process this information and try to estimate the size or change in diameter, and finally develop the risk score to differentiate our benign and malignant tumor. So this is a method I use to estimate my size. So for the purpose of size estimation, we use 3D interpolation model, and in our case, we developed a third order polynomial surface. Actually, it is developed, and this surface has been developed based on the experimental results or data we have. So this size estimation process find the relation between the size of the tumor with the force and the sum of the pixel intensity for multiple surfaces. Here the IJ index is the number of 2 and 1. So this is actually the main contribution of our experiment. Tactile imaging system can get the force, time information, but here we try to import vibration in our system, and we notice that it causes some change in the diameter of our tactile images. So for each session in our experiment, we record 50 images, 50 tactile images, and to estimate the size, firstly, this is our tactile image, and then we convert it into a binary image for some threshold value. So now we have the binary image. For every experiment, now we have 50 binary images, and for 50 binary images, we calculate the major and minor axis average. So now we have 50 diameters for 50 binary images. Now taking the average of all the binary images, we get the final diameter of our tumor. So the first case is the diameter estimation for without vibration case, and the second is for the with vibration. So now we have the diameter BWU for without, and now for with. Now we take the difference of two diameter and get the difference in diameter. So further, we use this diameter difference to calculate our final risk score value. So we say that we change or vary our frequency from 0.4 to 0.6 megahertz. So from this range, we have to find the optimized frequency. But how? That's why we consider these features, the diameter change. If we look, the first, we have two experimental sets, and the red line defines the benign one and the blue one defines the malignant one. In normal sense, we have tried to differentiate the benign and malignant one. That means that features that we will collect from them, that has to be much more further separated, so that the benign one will be benign and the malignant will be malignant. So with vibration, we get a great separation between the benign and malignant one. And from this range point, 4 to 0.6, we have the largest separation in 0.6 megahertz. So we can say that in our range, that means for our experiment, 0.4 to 0.6 megahertz, 0.6 is the optimized frequency for our experiment. Now we have the size and we have the optimized frequency. Now we calculate the diameter or change in diameter for this optimized frequency. So the first one is the benign case and the second one is the malignant tumor case. You can see that without vibration and with vibration, there is not any significant change in case of benign tumor. But in malignant tumor, this is for without vibration and this is for with vibration. So there is a huge change in the tactile image. So for these two cases, we calculate the diameter change. But in sense, we say that with vibration or with ultrasound wave, we find greater diameter change or greater change in our malignant tumor. So now we have the information of size, and then we calculate the change in diameter value. Now we want to develop the risk score value, because risk score value is one of the main parameters to differentiate our benign and malignant tumor. So it can range from 0 to 5 or 0 to 10. In our case, we keep the range is from 0 to 5. And for the minimum is defines the benign and highest is the malignant. So we have to find the threshold value so that below this threshold value, the tumor will be benign and higher is the malignant. So we calculate the risk score value by using this formula, where this is the estimated size and diameter change is defines the diameter, and RMS is the maximum risk score value 5. So using this formula, we have the final result as this is our true tumor information. This is our true tumor size, and these are estimated size, diameter change. And you can see that in case of benign tumor, the diameter change is quite smaller compared to the malignant one. So whenever we calculate the risk score value, these are the risk score value, and we say the threshold value is 3. So the first one is less than 3. That means these are the benign one, and the lower one is the malignant one. So our classified tumor matches our true value of the tumor. So actually, this small set of our developed algorithm are based on this small set of samples. So in conclusion, you can say that we developed a Vibro-Acoustic Technology system and developed the algorithm to calculate the change in diameter. And based on this information, we calculate the risk score value to finally differentiate our benign and malignant tumor. And finally, we can say that with vibration, the overall tissue characterization process has been improved. That means the accuracy of the tumor characterization has been improved. So these are the references I use for this slide. Thank you very much for your attention.